Look, if the two events are independent, it doesn't imply that those are mutually exclusive. What do you mean by mutually exclusive? And if two are mutually exclusive, it doesn't imply that those are independent. In this case, what is happening? Both the events A and B are mutually exclusive, but it does not imply that those will be independent or not. We'll see some examples where A and B are mutually exclusive, but still uh, may happen that they turn to be independent. Okay, fine. We'll quickly write down this result. This is a very, in the form of a remark, we will write this down. The remark is, if A and B are independent events, if the first one, A and B are independent with probability of A and probability of B both non-zero, then A and B can be mutually exclusive or not. What do
No,
you
sir.
think?
Yes.
Yes, they can be
No, sir.
mutually exclusive?
No, sir. No.
No. Why no, Manas?
So because there is no intersection between them, no intersection element, and for them to be independent events, the product of the individual probability should be equal to the probability of intersection. But here it is given that both are non-zero, so the product cannot
Exactly.
be zero.
So A and B cannot be mutually exclusive. So Saurav, your question was, yeah, in that question there was no intersection,
Hmm.
right? There
Yes.
was no intersection, and uh, the therefore they cannot be independent.
Hmm.
So the remark says that if probability of A and probability of B are non-zero, then A and B cannot be mutually exclusive. A and B are independent events with non-zero probabilities. Then they cannot be mutually exclusive. So if A and B are zero, then we can think of something. Okay, the result number two, if A and B are mutually exclusive, mutually exclusive with probability of A and probability of B both non-zero. Then A and B, yes, what can you say about independence?
So they can be independent.
No, sir. The same thing. It can never
But
be.
but so zero is there na?
Non-zero.
Oh, okay, yeah, non-zero. Then same.
Then A and
Cannot be
B
independent.
cannot be independent.
Independent.
Okay. So as they are saying that probability of A and probability of B are non-zero. So probably, and if A and B are both mutually exclusive, so A intersection B is equal to 0. Okay. But if they need to be independent, then probability of A intersection B has to be equal to probability of A into probability of B. But in this case, what will happen? This is a non-zero term and this is a zero term. Okay, so they can never be independent. Such type of events which are mutually exclusive with probability of A and B non-zero. They cannot be independent. Fine. Next theorem. These are small identities which are important while solving examples. Suppose A and B are two events defined on a sample space if A and B are independent events, then first one, A and B complement are independent. Second, A complement and B are independent. And third one, A complement and B complement are independent. Yes. What we need to show in the first case, probability of A intersection B complement this is equal to probability of A into probability of B complement. That is what we need to show. Let's draw the diagram. What fact we will use? A and B are independent events. Okay, that fact I will use. So there is A, there is B. What we have? A intersection B complement. What is A intersection B complement actually? Look at the Venn diagram and quickly tell me.
A minus A intersection B.
A minus A intersection. So probability of A minus probability of A intersection B. But what do we have? What do we have? A and B are independent events. So this will be equal to probability of A intersect into probability of B. I can take probability of A outside. In bracket, what I will have? 1 minus probability of B. What is 1 minus probability of B? Apurva?
B complement.
Probability of B complement. Similarly, you can prove the probability of A complement intersection B as probability of A complement. I'll leave this as a exercise. Probability of A complement intersection B complement. Yes, tell me. So this is probability of A union B total complement by which law?
De Morgan's law.
De Morgan's. So probability of A union B complement is nothing but 1 minus probability of A union B, right? Which can be written as 1 minus in bracket. What is the formula? Probability of A plus probability of B minus probability of A intersection B. Now what we will have? What is probability of A intersection B? What is probability of
P A dot
Probability of A into
A
probability of
to B.
Yeah. Probability of A probability of B. We open the bracket, we'll have 1 minus probability of A minus probability of B plus probability of A into probability of B, which is nothing but 1 minus probability of A into 1 minus probability of B. Just probability of A complement into probability of B complement. Okay. So if what do we learn from this theorem? Please summarize it and understand it properly, that if A and B are independent, then so are A and B complement, A complement and B, and A complement as well as B complement. So very important theorem.
Sir, can you show the last step? Done, sir.
I'll write down the independence for 3 events and then we'll go for examples. Independence of 3 events. So there are 2 types in this. The first definition, which talks about mutual independence. of three events. So mutual independence of three events A, B, C, which is also called the complete independence of the three events ABC, defined on a sample space sigma, defined on sample space sigma is defined as probability of A intersection B. This is equal to probability of A into probability of B. Probability of B intersection C is equal to probability of B into probability of C. Probability of A intersection C is equal to probability of A into probability of C. And probability of A intersection B intersection C is equal to probability of A, probability of B into probability of C. So this if some three events ABC defined on a sample space satisfy these three conditions, then what I can say, those are completely independent events. And the another definition is mutually independent or pairwise independence. Pairwise independence. So ABC defined on sigma, defined on sigma are said to be pairwise independent if yes, logically logically what conditions should be there?
The intersection of any two
Yeah,
events.
intersection of any
Probability
two
of
events.
intersection
So probability
should be
of A
equal to
intersection B equal to probability of A, probability of B. Probability of B intersection C is equal to probability of B, probability of C. Probability of A intersection C is equal to probability of A into probability of C. Then we say that the events are pairwise independent, but for being completely independent, there is one more condition, which is intersection of all three events ABC, and that has to be equal to probability of A, probability of B, probability of C. Clear? So we'll solve some examples now on independence of the events. Example number 1. If A and B are independent events. With probability of A equal to 0.5 and probability of B is equal to 0.4. Then find first one, probability of A union B. Second one, probability of A intersection B complement. Third, probability of A complement intersection B. And fourth one, probability of A complement intersection B complement. Yes.
Sir,
Hmm.
for the first one, probability of A union B, it is going to be P of A plus P of B minus P of A intersection B, the formula.
A union B is equal to P of A plus P of B
Minus P of
minus
A intersection B.
exactly. What is probability of A intersection B?
Probability of
PA
A into
into PB.
probability of B.
Yeah. Plus 0.4 minus probability of A into probability of B. So which is 0.9 minus 0.2. So this is 0.7. This is probability of A union. Second one, probability of A intersection B complement.
So it is probability of A minus probability of A intersection B.
That is one way, other way.
So
Probability of
probability
A
of
into
A dot
probability of
probability
B.
of B complement.
Exactly. So probability of A is 0.5. So it is 0.5 into 1 minus 0.4, 0.6. Similarly, we can take probability of A complement intersection B as probability of A complement into probability of B because A complement and B are also independent. Probability of A complement is 0.5 into probability of B 0.4, whatever the product is. And fourth one, probability of A complement intersection B complement is also equal to probability of A complement into probability of B complement. Probability of A complement is 0.5. Probability of B complement is 0.6.
0.6.
What are the products?
0.3
0.3.
and third one is 0.2.
The last one is also 0.3. Example. A machine consists of two parts. A machine consists of two parts. P1 and P2. Probability of defect in P1 is 0.08, and that in P2 is 0.05. What is the probability that assembled machine will not have defect? Assembled machine will not have any defect. Yes. First of all, you need to understand the experiment. What is the experiment? Then
So the probability would be probability of A complement intersection B complement. And
so you
these
need to
two events
define
are
what is A.
independent.
What is your A?
A is
So A is 0.08 and
Defective
A
part.
complement would be 1 minus 0.08.
No. You need to define the event first of all.
Sir, A
What is
will
your
be
event?
defect in part A, part 1, and B will be
Yeah.
defect in part 2.
So A is, I'll define my event A as P1 is not defective. Is not defective. What is the probability of P1 being defective? Probability of the part P1 being defective is 0.08, right? So probability of A will be equal to 1 minus probability of P1. Probability of P1 defective. Am I right? And so this is equal to 1 minus 0.08, which is 0.92. I'll define my event B as P2 is not defective. Is not defective. So what is probability of B? Equal to 1 minus probability of P2 defective. This is equal to 1 minus 0.05. So which is 0.95. Are the two events independent?
Yes, sir.
Why?
Because the ability of being defective of one part does not depend on the other part. Like if the second part is defective, then first part should be defective is not compulsory.
Yes. So what we need when our machine is going to be not defective, when there won't be any defect in part 1 as well as there won't be any defect in part 2. So required probability is equal to probability of A intersection B. But A and B are independent events, so this will be probability of A into probability of B. So this is 0.92 into 0.95. So that is
0.874.
8740.
Sir,
Yes.
sir, I understood that we had to find out the values of P of A and P of B, but required probability, can you tell how did we do?
When your machine is going to be working, I mean, when you can say that there won't be any defect in your machine, when will that happen? Read the question. Machine consists of two parts P1 and P2, probability of defect in P1 and probability of defect in P2. What is the probability that assembled machine will not have any defect? So a machine is going to be defect free if and only if there is no defect in P1 and there is no defect in P2. And I have defined my event A as there is no defect in P1 and I have defined B as there is no defect in P2. So probability of A intersection B is going to give me the probability when my machine is going to be defect free. Clear?
Okay, clear.
Yeah. Fine then. That's all for today. In the next lecture, we'll solve some more examples and also define the conditional probability.